Good afternoon, everybody. It is my pleasure today to introduce my friend and colleague from SFU, Anders Knudby, and his student, Derek Ho. They're going to be talking to us about the development of using remote sensing data and surface observations to try to develop a map of urban hotspots for the Lower Mainland area. So welcome, you guys.
Thank you. Yeah, so I'm Anders, that's Derek. What you see on the first slide here is actually sort of the end product that we have so far. It's a high-resolution air temperature map of Vancouver. So I'm sort of starting with the end, and everything from here on is going to be how we made this map, essentially. As I'm sure you're all aware, temperature matters. We have here an interesting map of most of Europe. What the map shows you is some areas in red where it got really hot in July 2003. And there are some blue areas as well where it wasn't as hot. What it specifically shows is a comparison of the average daily surface temperatures for July 2003 compared to July 2001. So what we see that France, parts of the UK, parts of Germany, over to Hungary, got really warm in July 2003 compared to what they were in 2001. Up to 10 degrees warmer, and this is an average over the entire month. Now I want to make sure that I make it clear that this is a surface temperature map, not an air temperature map, so it's not what you would typically see in your forecast. The reason why it's a surface temperature map is that because those are relatively easy to make, and I'll show you how. You may also have seen a graph like this before, maybe even this specific graph. What it shows you is through the summer of 2003, daily mortality in Paris. And as you can see, as it gets really warm, so after July, we were into August, in the middle of August, the maximum temperature for a period of almost 10 days in Paris, up here, reaches close to 40 degrees Celsius. And also importantly, the minimum temperature during that same period, it never goes below 20. So that's a really long period of really hot weather in Paris. And as we can see in the bar chart, as a result, mortality starts going up. So this is essentially an area that the mortality aspect of heat is an area that I know very, very little about, but which I'm learning currently mostly from Sarah. But it is the reason why we're interested in mapping heat. We're not going to make maps of Europe like that one that I showed you, which was made by NASA. We're going to make maps of initially Vancouver. And we're probably going to expand to other cities after this, after we sort of figure out how to do this really well. The reason why we're interested in cities is because, as you can see from this global chart, the world population is urbanizing. So if we focus in on the few areas where most people live, we can narrow down the scope of our work and still hit the majority of people in the world. And that goes for Canada more than it goes for the rest of the world, actually. I just found this number. Statistics Canada says that 81% of Canadians are classified as living in an urban area. So if we can make these maps really well, just for Canadian urban areas, we have mapped out heat for 81% of Canadians. I think that would be pretty good. The other reason why cities matter is because they get hotter than anywhere else. This is known as the urban heat island effect. And this is a very, very nice illustration of what it looks like. The dotted red line is a sort of a typical temperature profile. You start from the left of the slide. You go from a rural area where it's reasonably cool, although this is portraying a summer day. And as you go into what's called the suburban residential areas, the air temperature increases. And the further you go in toward the city center, the more the air temperature increases. As you come back out again on the other side, the temperature decreases. So if we target cities, we not only get the areas where most people live, we also get the areas that are the hottest. So it makes sense to target cities. So again, that's what we want to do. We want to make maps of air temperature in Canadian cities, and we're going to start with Vancouver. This is just to, this slide shows you the context of what we're ultimately trying to do, because what we're showing you today is just a mapping of air temperature, but ultimately this is part of a larger study, most of which is related to Derek's PhD work. So once we have a really good map of air temperature for Vancouver, the next thing we want to do is we want to make a map of the population of Vancouver's vulnerability to heat. So I'm sure you are aware of or can guess factors that influence a population's vulnerability to heat. These could include things like age and socioeconomic status, and so on. And most of the information that we need to make these maps we can get from the census data. So if we can make a map of air temperature and we can make a map of population heat vulnerability, we're starting to have some pretty good maps. What we then also want to do is we want to relate the temperature and the vulnerability to mortality. We can do this through a statistical model. And if we have all those three, we can essentially start to make mortality maps. So we can say, if Environment Canada predicts that we're going to have a 33-degree day on Monday, we can make a map that will give a reasonable forecast for how many people are going to die where in Vancouver. That would be pretty interesting. It would be interesting in its sort of just as an academic exercise, but it's obviously also pretty useful for the people who need to respond to these health issues. So that's what we're hoping to get out of this ultimately. We are definitely not there yet, so the rest of my talk is going to be just the mapping of air temperature, but this is the starting point. To map temperature, we use satellite data. We partly do that because they're available for free and they are useful for this purpose, and partly because that's my background. The way it works is that the Earth emits electromagnetic radiation from its surface. It does this at all times from everywhere. We can detect that radiation using sensors that we put on satellites. Based on the intensity of the radiation that we see from a given area, we can derive its temperature. Now, I've underlined again surface temperature, like you saw on the NASA map, because that's what we can measure directly, or more or less directly. It's a little bit of a leap to go from the temperature of a surface to the temperature of the air that's above that surface. And we're going to show you how we make that leap. But first, we're going to map the surface of the temperature of the surface, because that's what we can do very easily and very well. I'm showing you some graphs here that are meant to illustrate the basic principle of how we can do this. So we focus on the red graph for a bit. The red graph illustrates the radiation that would be emitted by a surface that is 300 kelvins warm. So that's a pretty reasonable sort of summer temperature Earth surface. What we see is that the amount of radiation that that surface emits, which we see on the y-axis, depends very strongly on the wavelength of the radiation that we're looking at. So if we're looking at, for example, wavelengths at around 10,000 nanometers, we see that this surface emits quite a lot of radiation. 10,000 nanometers is a very long wavelength for most of the radiation that we work with in remote sensing. Just as a comparison, visible light that our eyes can see, has wavelengths somewhere between 400 and 700 nanometers. So for the visible light, we're all the way down here. So we can see that a normal Earth surface at 300 degrees Kelvin does not emit very much visible light. That's why it's dark outside at night. But if we can design a sensor, and we can, that can detect radiation that has wavelengths of around 10,000 nanometers, we can see that if we are detecting this much radiation coming from a surface, it's probably 300 degrees Kelvin warm. If it was only 280 Kelvin, we would instead see only about this much radiation. And if it was only 260, we would see only this much. And that's the basic principle that we use. We put a sensor in space that can measure radiation at around 10,000 nanometers. And we see how much radiation comes from different parts of the Earth's surface. Now, specifically to find out what the temperature of that surface is, we have to use Planck's law. And the way we use it is way simpler than what it looks like initially here. Because, as you'll notice in my explanations here, h is Planck's constant, so it's a constant. C is the speed of light, so we're going to say that that's constant. K is Boltzmann's constant, so that's a constant. So we have three constants, essentially. We have h, c, and k, and you can see an h and c are repeated twice in this equation. So we have a lot of constants in there, so which means we can try to simplify it a little bit, which is what I've done here. So now you have a value there called K2, and K2, that's just my constant number 2. I've set that equal to 2hc squared, because that's a constant. And K1, I've set that equal to hc over k. So this is just a simplification. Nothing has changed. I've just changed how I label the constants here. So what this law tells you in a little more simplified form is that on the left-hand side we have spectral radiance. So in essence, the intensity of radiation that's emitted by a surface, given a certain wavelength, which is the lambda. So we have our constant 2 over, again, we have the wavelength that we're interested in here, raised to the power of 5. Our other constant, and we have wavelength. E is a constant. And then we have T here, which is the surface's temperature. So essentially what it says is that the amount of radiation emitted by the surface depends on the wavelength we're interested in and the temperature. Now, if we have a specific sensor in space that measures radiation at a specific wavelength, we know what that wavelength is. We can plug that number into this equation, and we can simplify it even further. So just as an example, say we measure radiation at a wavelength of 10,000 nanometers. We put in 10,000 nanometers into our wavelength here, and we simplify it even further. So now we have capital K1 and capital K2. So now what this law says is that the amount of radiation that we'll see depends on nothing but the temperature of the surface. So this isn't exactly the way that we use the formula in remote sensing, because what happens in remote sensing is that we have a measurement of L. We know what L is because we've measured it from different places at different times. So we want to isolate T, find out what is the temperature that corresponds to a given radiance measurement. And that's what we've done here. So this is just a rearranging of the last equation. So now you can see when you have your satellite image, for every little area on Earth, if you have a measurement of radiance, which is what we have here, you just plug it into this equation and it translates into a surface temperature. It is really not quite that straightforward, but as a basic principle, it is. There's a couple of complicating factors. Planck's law, which was the equation we just looked at, that works for a black body. A black body is a perfect emitter. So it's an object or a surface that, given its temperature, emits as much radiation as it can. In other words, it emits radiation according to Planck's law. All real-world objects are not black bodies. Black bodies are hypothetical. They don't exist. What we need to do then is we need to find out how close is the surface that I'm actually looking at now? How close is that to being a black body? So we can quantify something that's called the emissivity of the surface, which quantifies how much radiation does this surface emit compared to how much it would emit if it was a black body. In essence, how far away from conforming to Planck's law is my surface? So I have here a list of typical emissivities of standardized surface types. So for example, if we see the top one and the bottom one, wet snow and seawater, they have emissivities somewhere between 0.98 and 0.99. In other words, they are pretty close to being black bodies. An emissivity value of 1 would be that of a black body. So they don't emit quite as much radiation as we think they would if we just apply Planck's law, that equation, but almost. So if we're looking at those surfaces, we can pretty well get away with just applying Planck's law. If we're looking at, say, dry vegetation instead, we have emissivities that are down at around 0.9. So the surface, dry vegetation at a given temperature, only emits around 90% as much radiation as we would think it would if we were just using Planck's law. So that becomes more of a problem. If we're looking at more artificial materials, like glass has an even worse or even lower emissivity. And if we go to an extreme case, aluminum foil has emissivities that are really, really low. Aluminum foil can get really, really warm, in other words, without emitting very much radiation. If we have time at the end, ask me about aluminum foil and how you can use it to commit crime. If we know what we're looking at and we know what its emissivity is, we can just plug the number into the equation. And this is the little epsilon I've put in here. This is where we would put it into the equation. And luckily for us, there's some very smart people at NASA who are busy making an emissivity map for the world. And this is their North America, this is how much they've gotten done for North America so far. So you can see Canada is pretty well covered. If you can find Vancouver on this map, you can see Vancouver is actually fully covered. You notice that it has kind of a stripy appearance, which is because all of these data are based on other satellite measurements, and the stripes are kind of parallel to the satellite's orbital tracks. So occasionally for some orbits, when the satellite has passed over, maybe it was cloud covered every single time this one satellite passed over, so they haven't gotten the right measurement yet. But at least for the Vancouver area, we have very good emissivity data. So for any area we're looking at, we can basically take an emissivity value from here and say, we're going to use that value to put it into Planck's law and help us get a better temperature estimate than we would otherwise have. So that works reasonably well. You'll notice that there's no value for the ocean in this map, which is because it's a nearly constant value, so they didn't feel like putting it here. That's the one problem. We can solve that reasonably well with this kind of data. The other and much bigger problem is the atmosphere, because the atmosphere, it says here, it absorbs some of the radiation that was originally emitted from the Earth's surface before we can get to measure it in space. It gets absorbed by the atmosphere. So that's a problem. The other thing with the atmosphere is that the atmosphere has a temperature in itself, so it emits radiation. And some of that radiation is emitted up towards the satellite. So in other words, we're measuring some radiation from the atmosphere that we didn't want because it's not related to the surface. And we're not measuring some of the radiation that we did want because it got absorbed before it reached the sensor. And the atmosphere also scatters radiation. So some of the radiation that was emitted either by the surface or by the atmosphere and may initially have been heading towards the sensor, it hit something in the atmosphere and it changed its direction. And now it's no longer heading towards the sensor, and therefore it's not going to be measured. Same thing can happen the other way around. Radiation was emitted, say, by the surface, and it was heading away from the sensor, but then it hit something in the atmosphere and got redirected right into the sensor. So there's a lot of problems with what the atmosphere does to radiation and how it relates to the measurement that we make and how that measurement translates into a temperature. So my graph here, it shows the atmospheric transmittance, sort of for model atmospheres. Transmittance being how much of the radiation that's emitted from the surface actually reaches the top of the atmosphere and is available in space to be measured. We can see this varies a lot by wavelength. So for example, if we look at 15 micrometers here, you'll notice that the unit for wavelength here is a little bit different. Micrometers are 1,000 times as long as nanometers, so my previous example with the 10,000 nanometers would be located down here. Now if we look at 15 micrometers, atmospheric transmittance is pretty close to 0. So any radiation emitted by the Earth at that wavelength is going to be absorbed before reaching space. It should not come as a surprise then that no one has designed a sensor and put it in space that measures radiation at this wavelength. It would be kind of pointless. If we move back to the 10 micrometer area here, or 11 and 12, we see that atmospheric transmittance is reasonably good, but it's nowhere near 1. If it was 1, it would be like the atmosphere didn't interact with radiation at all, and we could use our measurements without worrying about it. If we have a typical subarctic winter atmosphere, which is the top of these lines here, we have an atmospheric transmittance or wavelengths that are somewhere between 10 and 12 micrometers of maybe 0.9. So we're still missing 10% of the radiation that was emitted from the surface when we measured it in space. And we don't always have subarctic winter atmospheres, right? Typically, for our studies, we have something that's closer to a mid-latitude summer atmosphere, which is the second line from the bottom. So we actually have atmospheric transmittance values in this wavelength range of about 0.6. So of all the radiation emitted from the surface of the Earth, only 60% of it reaches space. The rest is absorbed or scattered. So this is a big, big problem. If we know what the atmosphere looks like at any given time, when I say look like, it means we know what its temperature is, and specifically we know how much ozone is in different layers of the atmosphere and how much water vapor is in different layers of the atmosphere. We know those things based on models of how radiation travels through the atmosphere. We can try to make corrections for the amount of radiation that would have been absorbed in the atmosphere before we measured it. We can sort of backtrack and say, this is what I measured, this is what my atmosphere looks like, so this is how much must have been emitted. I know I'm not seeing all of it because it's being absorbed, but I'm seeing some of it. And so we can make an estimate of how much was actually emitted. Much of the time, we don't have such data. And so there are other methods available that I'm definitely not going to go into that you can use to sort of approximate what the atmosphere looked like. And again, you can try to backtrack and see how much was actually emitted from our surface. Just to complicate things even more, both the emissivity issue and the atmospheric effect issue, they both depend on the sensor's view angle. And this is my only video, but it is going to show you what the view angle is. So here we have a sensor, a satellite orbiting Earth. It has a sensor looking down on Earth, measuring how hot different areas of Earth are. This is just an example, obviously. If I pause it the next time the sensor comes around. Oh, I can. Oh, there. Okay, I just made it. So you can see some areas of the Earth, like, say, this one right here. The radiation that the sensor sees coming from here, it's as if the sensor is looking straight down and seeing the radiation coming from there. But other areas are seen at quite an angle. The same kind of data, it's just that the satellite is getting information from different angles. And unfortunately, emissivity changes with angle. So, and it's typically reduced the further we go away from emission straight into space. So this area over here, even if it was identical in surface type, say we're dealing with dry vegetation here and dry vegetation here. This dry vegetation would have lower emissivity for the radiation that it's emitting in this direction. So if we get really nitpicky about things, we need to consider that. We haven't done that. More importantly, the atmosphere. You can imagine that the amount of atmosphere that radiation coming from here has to go through before reaching the sensor is smaller than the amount of atmosphere it has to go through coming from here. Because here it's going at an angle. And that matters a lot. So we get a larger amount of absorption of the radiation coming from out here than we do the radiation coming from here. So again, we're trying to do our best to deal with these issues. Lots of people are working on how to do this, so we're definitely not alone on this. I like this video because it also shows you, apart from all these problems, it shows you one of the really great things about working with satellite data is that we have, satellites don't fly that fast, by the way. But we do get rather quickly full coverage of the Earth with data from a satellite instrument. And most of these satellites, they go for a long time. Most of them, they have a design life of maybe 5 to 7 years, and many of them end up working perfectly for longer than that. Some of them fail after a few months, which is horrible. Some of them last for 15 years, and they just keep on trucking, just collecting data, downloading data, collecting data, downloading data. So it's an enormous amount of information that we get from them. There's a lot of satellites and sensors that we can use to map heat. The ones that we're working with are in the top row here. They're called Landsat TM and ETM+. And the reason why we're using them is because we get a very good spatial resolution. We typically quantify that as the cell size of the data that we end up getting. So all data end up being sort of in grid format. If you were to plot it on a map and zoom in really far, you could see little squares. The size of those squares for Landsat TM would be 120 meters on either side. And for Landsat ETM+, 60 meters on either side. And that's as good as it gets from space. You can buy, if you have a couple of million, you can buy instruments like this and put them on an aircraft and fly them at really low altitude. And then you don't have to worry so much about the atmosphere. And you get much, much higher spatial resolution. They exist, and there's a fantastic nighttime heat map of Calgary that has been created using instruments like this, but we don't have that much money. Landsat satellites, they come by Vancouver roughly every 16 days. Right now, there are 2 of them functional in orbit, and they're on alternate paths, so now we get an image every 8 days. We get no useful data if it's cloudy, which is a problem, right? Because if it's cloudy, what we see is the temperature of the cloud, not what we're interested in. So that's a bit of a problem. But on the other hand, we're mostly interested in studying really hot summer days, and they tend not to be so cloudy. So that works out well now. As you can see, there are a lot of other sensors with different characteristics. One that we could potentially use is the one on the next line here, Aster, which has a comparable spatial resolution. It's better in some ways. We don't have to go into what the number of bands means, but the higher the number of bands, the more accurate an estimate of surface temperature you can typically get. In theory, Aster comes by every 16 days, except it's not always on. Landsat satellites are always on, at least for Vancouver. Aster's not always on. It's sometimes on if somebody wanted data for Vancouver. So we could try to ask them to collect some data for Vancouver, and we would be competing in priority with everybody else. What that means is if you look back throughout the last couple of decades, Landsat data exists in enormous volume. You can pretty much get Landsat data every 16 or 8 days. Just go back through time, and they are there, and they're free, and you can download them. Aster data, not so. They're pretty patchy, which is why we haven't used them yet. There's a lot of other satellites and sensors that we can use. You can see they all have really low spatial resolution compared to what we're doing. So remember that map of Europe that I've put up that was made using the MODIS sensor, which is great for mapping Europe. To have a cell size of 1 kilometer, not a problem. But for mapping Vancouver, it certainly prevents us from getting anything sort of near the neighborhood scale. They may be able to complement each other though, and that's something we're going to look into in the future. For example, if you look at this one called Severi, the second from the bottom, it has a really poor spatial resolution, 3 by 3 kilometer cells. But the temporal resolution on the right-hand side, 15 minutes. So we can get an image from the sensor every 15 minutes, day and night, every day. So that can possibly help us look at things like which areas heat up faster, cool down faster, or slower during the mornings and the evenings. We can also get data from nighttime. One of the problems with Landsat is we get no data from nighttime. We always get data from around 10:30 a.m. from Landsat. So what you get looks like sort of like this. When you apply that equation that I showed you to Landsat data that you download for free, this is sort of what you get. This is a map of surface temperature. This particular image happens to be from July 31st, 2009, which was just the beginning of a very big heat wave that we had here in 2009. Those of you who were here, you can probably remember it. And you can see that it looks, I think, pretty reasonable. It looks like Vancouver, at least. And you can see some areas that are hot that maybe you would expect to be hot. And you can certainly see areas that are, like the ocean, for example, looks pretty cool. You'd expect it to be cool. So just sort of very quick visual examination. This looks right. It's actually really tricky to test whether this is right. So if you think of it, if we zoom in really far, like here, we can start to see almost individual pixels. And these are the individual cells. These are the ones that are, in this case, I think 60 by 60 meters. Let's say that, 60 by 60 meters. I can't remember if this is the 60 or if it's the 120. If you wanted to, say, go out and take some field measurements to find out if the temperature estimate in a given cell was correct, or how wrong it was, that would be really difficult because keep in mind this is surface temperature. And so what we're measuring here is an average surface temperature over a cell that's, say, 60 by 60 meters. You can buy instruments that are not too expensive that you can go out and use to measure surface temperature. They're like the in-ear thermometers that you can get. You point them at a surface. They use the exact same principle as the satellite uses. Measure how much radiation is coming from the surface, converts it into a temperature. But if you do that, you measure a very small area that's maybe a couple of centimeters in radius. What we're measuring here is a 60 by 60 meter area. So there's a lot of smart people working on trying to come up with good ways to test how accurate these maps actually are. And we're not doing that. We're just waiting for other people to figure it out. And in the meantime, we're doing something else. We think that visually this looks pretty good. As I mentioned in this slide, it's not perfect. We can see even just there's some striping. See the stripes here going this way. This is a problem with the sensor. We can't really do very much about this. This is a problem that is in the data by the time we get them. Although we can't see these stripes when we go in on land, you probably didn't necessarily notice them here, at least in the urban area, although you may have noticed them up in the mountains and out in the ocean. They're still there in the urban area. Right? We get so much other variation in this area that we don't see them. But they're still there. They're still affecting the measurements that we get for each area. So the map clearly isn't perfect, but it looks pretty reasonable, I think, in general. So this arrow up here is pointing roughly to downtown. For any of you who didn't know that, you need to take a geography class. Roughly downtown Eastside here, it looks pretty warm, although this, I think, up here would also qualify as downtown Eastside, less warm. But we can clearly see some warm patches and some less warm patches. Keep in mind, this is just for this one day. This doesn't necessarily tell us what it always looks like. We have UBC out here. I'm not sure exactly where we are, but we're somewhere close to this arrow. We see Pacific Spirit Regional Park here, nice and cool, right? Almost as cool as the water. We've got a lot of trees. They evaporate lot and keep the surface nice and cool. We see it doesn't come out super clearly here, but we see a couple of areas down here that are kind of cool-ish. They're on land. There's one here and there's one here. And I've just put question marks because I was wondering if anyone in the audience knew what those areas might be. Yeah? That's right. You play golf? Okay. So yeah, golf courses tend to stay nice and cool as well, right? Because even if we're in the middle of a heat wave, it's nice and hot everywhere. Golf courses are irrigated. So they stay nice and cool because there's all that moisture coming off, keeping the surface cool. So we can see things like this. Now, that wasn't really what we wanted, though. Right? This was, like I said, this is what was easy to do with remote sensing. We could map surface temperature. What we wanted to do was map air temperature. So this is my cue to hand it over to Derek, who's actually been doing most of the work on mapping the air temperature as opposed to surface temperature. So, hand it over. Go.
Right. So we see that we have first map the surface temperature map. So now talk about some problems of the surface temperature map. So look at this graph. The blue line is actually the correlation of the surface temperature and the air temperature, and the red line is the difference of air temperature between the urban and rural area, right? So actually, you see that in the earlier time, like in the morning time and afternoon time, the correlation between the surface temperature and air temperature is really bad, which is actually not really useful for the health study. So you may be able to use the surface temperature at the night time, like maybe 10 o'clock or 11 o'clock, which is 0.7 correlation rate. But sorry. So yeah, it's just closer, right? Sorry. Yep. But at the morning time, especially at the afternoon, 3 o'clock or 4 o'clock, right? The correlation is just 0.2 or 0.1, which is not useful for studying the heat health in the Vancouver. So that's why we try to map the air temperature because the correlation is actually bad. So actually, it's nice. Yep. And so in this case, right, we try to use more parameters for the model to map the air temperature. So previous study also noticed that like vegetation, especially the density of vegetations, and the moisture, and wind speed direction, also like the surface moisture, surface material, and structure is useful for mapping air temperature. So for example, like wind, if you are in a faster wind speed day or like a lower wind speed day, actually this affect your apparent temperature also for air temperature, right? So that's why we try to include this type of variables inside the model. So now we actually use some data in Vancouver from the Environmental Canada and also another network of weather underground. So what is weather underground is actually the which is a volunteer-based weather station. They are like people trying to use a personal weather station at their home. They measure the temperature and then they put it online so we can download it. So it's actually more useful for the public health study. Sorry, okay, sorry. All right. So now I think you can hear my voice right now. Anyway, yep. So in this case, right, weather underground is actually useful because they put the weather station at your home, right? So and then it's actually indicated the air temperature in the urban area, which is useful for the public health study. So environmental Canada is also good, but mostly they are located in the rural area. So now we get all the urban area data and the rural area data of the air temperature, so we can use that to map the air temperature. So in this case, right, we're still using the surface temperature, which is now it still have some correlation between the air temperature and surface temperature, although it's not as useful. And then we also combine with the vegetation moisture index from Landsat, which is we just talked about. They have some correlation between the vegetation and moisture. And you know that elevation, higher elevation is always like lower temperature, right? So we also include that into the model. And in the Vancouver, always like facing south is they get a higher solar radiation, which is like it heat up the temperature in the urban area faster than the Lofton when the house facing north. So that's why we also include these variables. And also the last one is the urban structure. So what is that? It's like in the urban area, because the building is so high, so they actually block the wind speed and then they change the wind direction, right? So actually it affect the patterns of air temperature. So we also include these kind of variables inside the model to try to make a better air temperature map. So we create a model based on statistical model and then predict the air temperature by using the daily maximum temperature in Vancouver in a typical hot summer day. And this is actually relative to the Vancouver International Airport. The reason is that we try to use that for doing some public health stuff. So we want to make a scenario which is like useful for the typical summer day. So if we try to use the relative temperature, it's actually better. So we try to apply all the variables here in from here to the models, and then we map the map, which is this one. So this time, the map actually also look reasonable because as I look at the where's the mouse is here, right? And then the downtown Eastside again, which is actually I think this place is close to Hastings, East Village, right? And then they get a hotter temperature. Downtown, which is a little bit colder, UBC here, and then I think they just point exactly on the population buildings, right? I guess. And then it's reasonable, it's cold, and then Grouse Mountain is cold too. And you can see that the temperature between the urban area and the mountain area is like separate. So I think it's okay. First of all, like some place like Lynn Valley, etc., is also hotter than the mountain. So I think this is reasonable. But it would be like if you have question about the map and then you find some place which is some problems, you can also tell us, which we can try to fix that later. That would be nice. Yep. So in this case, actually we make a map, but there's still something we have to do in the future. First of all, it's like the data control because first of all, the data is not collected by us. For example, like just go back here. So weather on the ground is a volunteer-based weather station, right? So we don't know how to collect the data. Although supposed to be they should be within the standard, but there should be some problems. Environmental Canada is actually located in the rural area, which is like they have the standard for the regional air temperature study, but which is not for the local climate study. So for the data quality, which is using for the public health, this kind of data may have some problem. So that's why that is a technical issue. Second of all is like the mobile temperature measurement. So I just mentioned that like Environmental Canada or the station is actually in the let's go back here, right? In the rural area, right? So you see that in Vancouver and Burnaby, we actually didn't have that much weather station. In Richmond is no data station at all. So that's why if you want to do the urban study, like the urban heat health study, we have to get some mobile temperature measurement around this area, like the Vancouver, Burnaby, Richmond, so we can actually get more data to map the air temperature, which would actually increase the accuracy rate. So again, sorry, I always mess up the PowerPoint. And then okay, so for what is LiDAR data for urban structure is like so LiDAR data is actually useful to build up the 3D models. So if we actually get the LiDAR data, so we can actually build up the whole 3D models of the building structure in the urban area, so we can know better about how those wind direction and wind speed is in the urban area, and also we can know how the solar radiation change in the urban area. Actually, it's really helpful for us to map the air temperature, and then, and as just Adam mentioned before, and different satellite image they have different overpass time. So now we are using Landsat, which is at the 10 o'clock at the morning time, which is actually not the hottest time in the at the day rate. So if we combine with other additional satellite image, maybe like MODIS or ASTER, we can actually map a better air temperature in the Vancouver. So this is what we're looking for in the future to fix the technical issue. doing the house study, minimum temperature and apparent temperature is actually useful. Some study actually use those minimum temperature and apparent temperature and maximum temperature and the average temperature to map to study the relationship of the heat mortality and the air temperature rate. So, but the problem beside the ambient temperature, actually, right now in remote sensing field, we still have no method to map the ambient temperature. So that will be a challenge for us to do that in the future. So that's why we say it's harder to map the ambient temperature, but it's easy to map the minimum temperature. So to produce the heat map for mortality and also the all the other health study is also useful. This is the aims of this project. So after we try to make up the air temperature map, like the minimum temperature, maximum temperature, and apparent temperature, we can also try to produce the heat mortality map based on this result, and then use that for doing the preparation as well as planning and etc. So I think this is the time I could get back to Anders.
See if I can get this one to work. Does this work? Yep. Yes, this is another thing that we were planning on helping out with. Essentially, I just very recently talked to people from the city of Vancouver, and I learned that they have an urban forest strategy, which I did not know of, where they aim to plant 150,000 trees by 2020, and they are that's the target. Where to plant them is a different issue. Obviously within city limits, but apart from that, they're free to do whatever they want. And so what they're trying to do now is to try and figure out where can we get the most cooling effect for the trees that we plant. And that has to be seen, you have to consider as well the cost of planting trees in different areas. So they want to come up with some kind of cost-benefit model where they can show we plant a certain number of trees in this area, we can get to cool down this area by so and so much, and it's going to cost us this much to do it. Or if we plant a certain number of trees somewhere else, we're going to get this amount of cooling. And of course, it's not just the amount of cooling. For example, if we could create some maps, for example, the mortality maps would be a good use for this. If we can show them that next time we have an extreme heat event in Vancouver, this is where how many people are going to die if it's such and such an extreme heat. We can then go in and say, if you plant 50,000 trees in this area that has a very vulnerable population and already gets really hot, this is essentially how many lives we're going to estimate that you can save by planting those trees. That would be pretty interesting, I think. That's a lot of extrapolation and guesswork that's involved. So they would be very sort of weak estimates that we could make. But it would be better than having no information of this kind at all. So this is a very immediate use, I think, of our work. Let me just go back here and see. Yeah, and the other big thing, obviously, is once we have this working pretty well for Vancouver, the replication in other areas is going to be key. Because let's face it, Vancouver is probably not the city in Canada that gets the most heat. So there are probably other areas that are at least as interesting to do this kind of study in. And we're already trying, for Sarah and some of her colleagues, to expand in that way. So that's what we have for now. Do we have time for questions? Or yeah, okay. Okay. Yeah. It's on.
Yes, hello. Thank you for this joint presentation. It was really interesting. I have a question with regards to those limiting factors that you were explaining, and one of them was the emissivity that you're taking from the NASA. So you're not calculating it. You're taking data that's given to you, right? What I'm wondering is, in a city like Vancouver and other cities where it's booming and there's all this construction going on, how stable in time? Or in other words, how confident are you using those numbers?
Yeah, that's a great question. What we have now is a one-off fixed layer. So I think I can best answer it by going back to look at this table here that I had. Not that one. There. So essentially, it depends on if we see a change in surface type in a given area. It depends on what kind of change it is we're seeing. As I think my bigger worry, rather than urban expansion and so on, is the seasonal changes that we're seeing, right? So I have different numbers here for healthy green vegetation and for dry vegetation. Different numbers for wet and dry snow or no snow. And so emissivity obviously does change a lot throughout the year. Now, if we're looking specifically at hot summer days, I'm going to say the vegetation is probably going to be fairly dry. So we're going to assume that works. But we don't actually know whether the data that we have in this layer for a vegetated area, we don't know whether that is meant to represent when the vegetation is dry or when it is moist. So yes, that's a problem. I can answer it very briefly, actually. We haven't dealt with it at all. This is the only thing we have available. We felt that this was better than nothing. Although, honestly, I'm not sure how much better than nothing, because there's another interesting aspect. You know what? And so I thought about this lately. It may actually be worse than nothing, and I'll try to explain why. Because what we're ultimately trying to do is not to map surface temperature, right? Which is what this helps us to do. This helps us to correct for this problem in Plancks Law and get a very good estimate of surface temperature. But what we are more interested in is when we have a hot surface, it emits radiation, and some of that radiation is absorbed by the air immediately above it and heats up the air. So rather than the surface's temperature, we are really more interested in the amount of radiation that comes off that surface. And by using emissivity in our calculations, we're actually taking that factor out. If we ignored emissivity, we'd have a more direct measure of how much radiation comes from a given surface. So we could look into that. We could look into just removing this. There are a lot of things we could look into, so we may do that at some point.
I think I see a bunch of questions popping up from the online audience. I will check. Okay. Would a network of surface-based temperature sensors be able to provide cleaner data, such as and is such a network practically achievable?
I think depends on the network. It's going to be my stock answer. It depends. Let's go here to see, because you could sort of argue that more or less what we have here is a network of ground-based sensors, right? That is actually what we have. So all these little green and red dots in this map show Environment Canada weather stations in red, and this weather underground, the personal weather stations in green. If we had a really great network that was much denser than this, we may be able to just interpolate between each station in that network and get a really great map out of that. In the absence of such a network, I think this is the better approach.
Question from the online audience. Very interesting work. Do you know if Environment Canada is interested in generating high-resolution temperature maps for major urban areas on a daily or hourly basis? You could feed active weather station data to the underlying model to generate daily or hourly maps.
That is a good question. I do not know whether Environment Canada is interested in this or not. But I do know people at Environment Canada, so I will check. Um, one interesting thing I can say about Environment Canada is when we started using all of the data from their weather stations, um, we started looking at the sites that they had put weather stations in. And they're following some criteria that have been put up by the World Meteorological Organization for how to put a weather station in a proper place. Like you don't put it right next to a vent or an AC outlet or something, right? You put it ideally out in the middle of an open field, a certain distance away from buildings, a certain distance away from anything else that might affect the measurements. But what's interesting about those criteria is that they pretty much prevent you from putting weather stations in urban areas. And you may be able to see this pattern here in the map. If you look at all the red dots, it's not that clear, but at least you can see in Burnaby, right? Environment Canada, or around where the label Burnaby is. Environment Canada has no weather stations there. And part of the reason is that they can't put one there that conforms to the criteria that they need. And the reason why Environment Canada doesn't do that then is because they're not actually particularly interested in the small-scale distributions of humidity and temperature within an urban environment. They're trying to get measurements that they can use as inputs for their weather models. They want to look at large-scale air masses and movement, and therefore they don't necessarily want measurements that are from a certain neighborhood, that are very localized in nature. They may be interested in doing that, but at least currently their data collection strategy doesn't suggest that.
Thanks very much. That was a great presentation. I just wondered, given that the source of the energy is the sun, so if you study it with like a black body, you would have people heating all over. So all of this variation is basically coming from topology and buildings. And could you actually create a deterministic model where you actually put some kind of regression type, something fairly straightforward, at least to try and get an idea of maybe for, I don't know, for evaluation purposes or something? Or does anyone already do that kind of thing?
Yeah, in the in the scientific literature, there are a few models like that that try to they use simple sort of energy and radiative transfer principles to say this is how much energy is coming in. So they have input from the sun, and then they have input from a variety of human activities, and then they have outputs in various forms. And so the models seem to work reasonably well if you can provide all of the information that they need on a per cell level. And that's where, for an urban environment, it becomes really, really tricky to do. Because, for example, you need to have a pretty good idea of the amount of latent heat transfer into the atmosphere. You need to know how much evaporation is happening from a certain area. And that is largely determined by, obviously, moisture availability on the surface, but also by wind speed and by air humidity. And we don't have those data on a cell-by-cell basis. And therefore, we can't really make those kinds of models without huge simplifying assumptions, which other people then use, and they get reasonable results. And it's something that I've been talking to Derek about that we may want to try at some point. I think at present, we would get a less accurate result, but we might get a more interesting model, because what we could then start to do more easily would be try to manipulate it. So for example, with the tree planting issue, we could very easily plant some trees in an area, which means essentially increase the shading and increase the evaporation, and see what happens in sort of a simulation sense. So I'm very interested in doing that. But I don't think at this point that we would get necessarily a more accurate air temperature map out of it.
Okay, thank you very much to Anders and to Derek. We'll let you go.
All right, thanks.